Definition of the derivative at x equals a. We are now entering one of the two main branches of calculus, differential calculus. So what is a derivative? So a derivative is the limit of a difference quotient. The derivative represents instantaneous rate of change. And the derivative at a point is the slope of the tangent line at that point. So we want to understand all three of these definitions of a derivative. We just finished saying that a derivative is the slope of a tangent line at a point. So what is a tangent line? Informally, a tangent line to a point on a curve is a straight line that only touches the curve at a single point, near that point, and touches or grazes the curve. So here we have a graphical example. So we have this curve over here. We'll go ahead and call it some f of x. And our point is the x value a and the y value f of a. So a tangent line just barely grazes the curve, just sort of taps the curve near that point. So what does it mean near that point? So in other words, the graph could be turning around and coming down over here, and this line extends. It doesn't matter that it intersects over here. So we just need it to sort of graze the curve near that point a f of a. In this example, we're going to draw tangent lines to this graph of f of x at each of the following x values. And then we're going to determine whether their slope will be positive, negative, or 0 at each x value. So we're going to start with the x value negative 6. So what it means to be a tangent line, again, we have to find the function, so it's down here, and we want to go ahead and draw a tangent line at the value on the function, so that would be right down here. So this is my point of tangency. So a tangent line, a line that just barely grazes the curve right there, is going to look something like this. So we're going to analyze, is that slope positive, negative, or 0? Well, that is a negative slope, so I'd go down and over. So I'm going to go ahead and classify this as a negative slope. So I'll just write a little negative sign here. Let's go ahead and move on to negative 2. So at the x value negative 2, I'm going to find the function right here. I'm going to draw my point of tangency and sketch a little tangent line, a line that just grazes the curve. And recognize that that line would have positive slope. So over here, I'm going to go ahead and write a little plus for positive slope. And we'll continue on at x equals 0. Looks like I'm going through 0, 0 as my point of tangency. And I'm going to draw my tangent line that just barely grazes the surface. Again, I have positive slope. Over here at the x value 2, the next value, I'm going to go ahead and draw my point of tangency. If I drew a tangent line over at 2, it looks like this one is going to have negative slope. And we'll move on to x equals 4. So over here, x equals 4. So 4 would be right here, that point of tangency. So this tangent line is actually going to be perfectly horizontal. If I want to just graze the surface of this curve, I'm going to have a perfectly horizontal line which has a slope of 0. So at x equals 4, I have a slope of 0. And then finally at x equals 7, so I'm going to go ahead and label this tick mark as 7. I'm going to find that point of tangency up here. And if I draw my tangent line that just grazes the surface, again, I'm going to have positive slope. So now the question becomes, how are we going to find their exact slope without a second point on the line? So we know how to find the slope between 2 points. We have a formula for that. y2 minus y1 over x2 minus x1. But for all of these little tangent lines that we've drawn, we only have one point on the line. So we only have one point that we know from the function itself. We'll be able to get that x and y value from f of x, but how are we going to get some other point on these tangent lines in order to find the exact slope? That's the question. Well, here's what we're going to do. We're going to be using secants to find a tangent. So what is a secant? A secant line is a straight line joining 2 points on a function. So what we're going to go ahead and do is take a look at an example of this over here. So here I have a function f of x, and I have 2 points on that function, which are labeled over here as a f of a and x f of x. And that line that connects those 2 points is my secant line, so it goes through 2 points on a function. So we are able to find the slope between those 2 points, and that has a special name called the difference quotient. So the expression, the change in f over the change in x, so this is delta change, or the change in y over the change in x, that's subtracting the 2 y values. So this is like y2 minus y1, f of x minus f of a, all over x minus a. So it's like x2 minus x1, that familiar slope formula. And again, this is called the difference quotient. So I just want to make one small note here that we're talking about secant lines and tangent lines, and these are completely different from, if you've taken trigonometry, the secant function and the tangent function. So as I said, we are going to use secants to find the slope of a tangent line. So what we're going to do is observe over here on this first graph that we have this point P, and point P has a tangent line running through it. And then we have another point over here, Q, and so we have a secant line passing through P and Q. So the goal is to find the slope of the tangent line, this line here. And the way that we're going to do that is we're going to observe, we're going to notice over the course of these images that if we move the point Q closer to the point P, or as labeled on the x-axis, as the value x approaches A, we can see that the slope of the secant line between P and Q is getting closer to the slope of the tangent line that passes through just the point of tangency P. So this last picture kind of sums up what's happening. As x gets closer and closer to A, so this value Q moves along the curve, or this point Q moves along the curve, I'm going to get a better and better approximation of the slope of the tangent line that passes through the point of tangency P using secant lines. And now finally, the last thing we're going to do here is we want to define a variable for the distance between A and X that's getting smaller and smaller. So what we're going to do is we're going to call it H. So if I look over here, what's happening here is I'm defining this distance H between A and X. So that would mean that this distance right here is H, which means that X is A plus H. So we're essentially naming Q the point A plus H, and then F of A plus H. That's the coordinate point Q, and P stays the same. It was A F of A. So we're just giving a new name to Q. Instead of X F of X, we're calling it A plus H F of A plus H. And so our difference quotient is going to look a little different. This time, my y2 minus y1 is going to be f of a plus h minus f of a, that's the numerator. All over my y2 minus y1 is my a plus h minus a. But notice what happens in the denominator, a and minus a cancel, and I'm going to get just an h on the bottom. So this is an alternate difference quotient that allows us to use this new variable h, where h is that distance along the x-axis that we're trying to shrink. We want to get that down to 0 so that those secant lines are used to approximate that tangent line, or eventually find the exact slope of the tangent line. So now we can formally define a derivative at x equals a. So the derivative of a function f at x equals a is the limit of a difference quotient. So the notation here reads f prime of a, so the derivative of f at the x value a, is going to be the limit as h approaches 0. So remember what h was. H is that distance between those two x values. if that distance h is going to 0, so it's getting really, really small, we can see in the second picture as well, as x is getting closer to a, so that value of h is shrinking, over those slopes of secant lines, then that's going to actually give us the exact slope of a tangent line. So that is the definition of the derivative at a point. It's the limit of a difference quotient. And when this limit exists, we say that f is differentiable at that x value a. So this up here is one version of the definition of the derivative as the limit of a difference quotient. We also have an alternate formula for the derivative at x equals a. So f prime of a again, or the derivative of f at a, an alternate definition says the limit as x approaches a, so we go back to that original difference quotient, x approaches a, of f of x minus f of a over x minus a. So both of these give us the formal definition of a derivative as represented by the limit of a difference quotient. In this example, we want to set up but do not evaluate both versions of the limit of a difference quotient to find the derivative of f prime of 1, given the function f of x equals the square root of x squared plus 1. So these are the two versions of the limit of a difference quotient, and we're going to go ahead and make sure we can set both of them up. So we want to find f prime of 1, so that's the a value. So we'll go ahead and work on the left side first. So anywhere there's an a in my limit of a difference quotient for the left-hand side, I'm going to go ahead and replace that a with a 1 because I am attempting to find f prime of 1. So that's going to give me the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. And that's the first step, but now we have to actually apply the function f of x. So I want to first find f of 1 plus h. So I'm going to work on this piece over here first. So I'm going to work on this portion right here, f of 1 plus h, which means that I'm going to have to substitute in 1 plus h into my function f of x, into the x value. So 1 plus h replaces this x. So I'm going to have to keep the limit. So I have the limit as h approaches 0, put a big fraction bar here. So I'm working on the top left side, so it's going to be the square root of 1 plus h squared plus 1. So I've just done that first part here. So those two parts coincide with one another. And then I'm going to go ahead and put minus, and I'm going to work on the next part. I'm going to work on f of 1. So that means I'm going to need to plug in a 1 into the x value in the f of x function. So f of 1 means I'm going to have the square root of 1 squared plus 1. So I have the square root of 1 squared plus 1. So now I've done that top right part of the difference quotient, and then it's just all over h. So now I've officially set up the difference quotient. We can do a little more simplifying. Doesn't mean we have to solve it all the way, but a little bit more simplifying would take us to the limit as h approaches 0 of the square root of, inside the square root symbol, I'd have to distribute 1 plus h times 1 plus h, so I can't distribute the exponent, but I can write this as h squared plus 2h, and then it's going to end up being plus 2 minus the square root of 2 all over h. And so that's done with the setup and a little bit of simplification for the first limit of a difference quotient. And then we'll go ahead and do the same thing with the alternate version of the limit of a difference quotient. So I still have the a value of 1, so everywhere in our alternate limit of a difference quotient, we're going to replace the a with a 1. So f prime of 1 equals the limit as x approaches 1 of f of x minus f of 1 over x minus 1. And now we're going to go ahead and apply the function f of x. So here we're going to go ahead and replace that top left part, f of x, with the exact function. So in our second line, we're going to have the limit as x approaches 1, f of x is the square root of x squared plus 1. So that corresponds to that top left part, and then we're going to have to do minus f of 1. So f of 1, we actually already found f of 1 over here on the left-hand side. So f of 1 was plugging 1 into the x, and it simplified to radical 2. So we'll go ahead and just go straight to putting radical 2, or the square root of 2, all over x minus 1. So this is the setup of my alternate limit of the difference quotient for the definition of the derivative at a point, so the point being the x value 1. So you can see they're not the exact same limit, but they would, however, give you the exact same answer. In this example, we'll work backwards. The following limits represent derivatives of f of x at some x equals a value. Find f of x and find x equals a. So we have the limit of a difference quotient. We have the derivative. So this is equal to f prime of some number. So we're looking for what is that number, and then what is that function f? What's the original function we're trying to take the derivative of? So we can see that I have h approaches 0, so I'm using this definition of the limit of a difference quotient. So that value of a is, in this example, going to be 2, right? I can see that a plus h happening, that 2 plus h. So looks like we are finding f prime of 2. So that x value is 2. And we're also trying to find what is f of x. So what are we plugging a plus h into? So we are plugging 2 plus h into the function x cubed. So 2 plus h is the inside function. It would be replacing the x in x cubed. And if we look at the second example, the limit as x approaches 2 of e to the x minus e to the 2 over x minus 2. Once again, we know this is the limit of a difference quotient, so it is the derivative at some value. And it's the alternate limit of a difference quotient. And I can see that the value of a is 2. I can see it in a lot of different places. That value of a is 2. So my x value is equal to 2. And I'm interested in finding f of x. Well, this one is actually a lot more straightforward. Finding f of x is just what is that function in that top left corner of the fraction in this case. So e to the x, or in the rational expression here, so e to the x is our f of x. Now here we're getting to a big example. So part A is asking us to find the derivative of f of x equals 5 minus x squared at x equals 1. So we're going to find the exact slope of the tangent line of the function 5 minus x squared, which is graphically shown here, at the x value 1 specifically. So we are going to find the slope of this tangent line here. So we can see that our answer should be negative. And first we're going to use this limit of a difference quotient. So f prime of a, or a is 1. So let's go ahead and set it up. We're going to do f prime of 1 is equal to the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. And then we go ahead and use the function f of x. So if I plug 1 plus h in, I get 5 minus 1 plus h squared minus, now I'm going to plug a 1 into 5 minus x squared, so 5 minus 1 squared. We'll be careful, we'll put parentheses around each piece in that numerator, all over h. And now we are going to evaluate the limit. We're going to go all the way this time, not just set it up. So in the numerator, we're going to have 5 minus, I'm going to keep parentheses. If I distribute, I get h squared plus 2h plus 1 minus, and then inside the parentheses I'll have 4, so minus 4 all over h. And I keep going here, so I have 5 minus h squared minus 2h minus 1, so distribute the negative, minus 4 all over h. And now, in the numerator, we have 5 minus 1 minus 4 cancels, that's 5 minus 5. So I'll go ahead and rewrite what I have going on left. I have the limit as h approaches 0 of negative h squared minus 2h over h. Now, if I were to try direct substitution, I'd end up with 0 over 0, indeterminate. So I'm going to have to use a little bit of algebra, and that's going to be factoring out an h in the numerator. So I cannot cancel unless I factor. So if I factor out an h, I'll get negative h minus 2 over h. And now, since the h's have been removed, in this next step, I can use direct substitution on negative h minus 2. So if I substitute in 0 for h, I end up with a slope of negative 2. And we can see from our original slope of the tangent line over here with negative slope that negative 2 is a plausible answer for that slope.
Now that we got out an answer, we can say, since the limit of the difference quotient exists at x equals 1, we say f is differentiable at x equals 1.
And just to show that we do get the same answer, we'll also evaluate the derivative using the alternate limit of a difference quotient. So f prime of 1 would be the limit as x approaches 1 of f of x minus f of 1 over x minus 1. So we'll substitute in f of x, which is 5 minus x squared, minus f of 1, so 5 minus 1 squared, over x minus 1. And in the numerator, we'll simplify. So we end up with 5 minus x squared minus 4 over x minus 1. I'm going to go ahead and move it up here and simplify at the same time. So I have the limit as x approaches 1. In the numerator, I have 1 minus x squared. In the denominator, I have x minus 1. So again, applying direct substitution, I get 0 over 0, which is indeterminate. So the algebra that we're going to use is factoring. And the numerator factors as a difference of squares to 1 minus x, 1 plus x over x minus 1. And now these terms, 1 minus x and x minus 1, they don't cancel perfectly. What's going to come out of that is going to be a negative 1. So I'm going to end up with a limit as x approaches 1 of, I have a negative 1 times 1 plus x. And now I can apply direct substitution. I will not get indeterminate. I'll get negative 1 times 1 plus 1, which is the same answer, negative 2. So now let's formally define what a tangent line is. So assume that f of x is differentiable at this x equals a. Then the tangent line to the graph of f of x at a passes through f of a and has slope f prime of a. So that means that we can write its equation as y minus f of a equals f prime of a times x minus a. And this should be a familiar formula. We can consider this an x1, y1, and f prime of a as a slope m. So this is really the formula y minus y1 equals m, the slope, times x minus x1. So nothing really new going on here. So let's go ahead and complete this large example by now finding the equation of the tangent line to this function we were working with, 5 minus x squared at x equals 1. So we had sketched the tangent line over here, and we went ahead and found what its slope was. So its slope was -2, so I'm going to write that off to the side. Its slope, f prime of 1, was -2. So that's like my m value. And then I need a point. So I need my f of a. So my a value was 1. To find f of a, I need to go ahead and substitute 1 into f, the original function, which we've done a few times now. When you plug in 1, you get out 4. So an equation of the tangent line is y minus 4 equals -2 times x minus 1. Now this is an equation. It happens to be in point-slope form, which is fine. If you're specifically told for a particular form, like slope-intercept form, then we should do a little bit of rewriting. So we'd get -2x, and then if I distribute the -2 and add the 4 to the other side, I get -2x plus 6. So for this example, either one of these is fine, but you always want to pay attention to the instructions if it asks for the line to be in a specific form. Now we're going to take a look at a theorem. The limit of a difference quotient definition can be pretty lengthy, so we're going to start to learn some shortcuts, and this is the first of many. So given a linear function, f of x equals mx plus b, the derivative, f prime of a, is just m, is just the slope for any value of a. So since it's already a linear function, the slope of the tangent line is really just the slope of the line itself. So informally, the derivative of a linear function is always the slope of the line. So a constant function, f of x equals b, has derivative f prime of a equals 0. The slope is 0 for all values of a that we choose. So informally, the derivative of a constant is 0. So two quick examples based on the last theorem. Given f of x equals 3x minus 2, find f prime of 1. Once we recognize this as linear, the answer to the derivative, no matter what the a value is just the slope of the line. So f prime of 1 is equal to 3. And here, given f of x equals 4, so this is a constant function, a horizontal line. So the derivative, f prime, at any value, including -2, is just 0. In this example, we're going to use the following graph of f of x to evaluate the following derivative. So I have this piecewise function here, and it's consistent of all linear pieces. And we're asked to find first f prime of -2. So let's just clarify, this is f of x. This is the original function f of x. I want f prime, the slope of the tangent line, at -2. So I can go up here and I can find the function, and it's a linear function. So I just need to find the slope of the line that that particular point is on. So the slope would be, I'd have to travel down 1 over 1, so my slope is -1. Moving on to f prime of 1, so I find the x value 1, I find the function, and I need to find the slope of that line. It's already a linear function. So the slope of that line, I have to travel up 2 over 1. So that is a positive slope of 2. And then finally, f prime of 4, so that the x value 4, if I find the function, it's a linear function, but it's actually a constant function with a slope of 0. So f prime of 4 is 0. In this example, we're given the graph of f of x. we're asked to compare the following derivatives by filling in the blank with either less than or greater than. So we're to compare these two slopes of tangent lines. So we'll draw each f prime of -4. So I want to be as accurate as I possibly can in drawing this tangent line. So f prime of -4 would look like this particular slope. So we do have a positive slope. And f prime of 0, so if we go over here to 0, looks like 0, 0, and I draw myself a tangent line, it's also a positive slope. So how do we compare the two? Well, here we can see that this slope at -4 is not as steep as the slope over here at 0. So I do have a steeper slope, which is a bigger number, right? The rise over run is a larger number here than it is over here at -4. So f prime of 0 is actually going to be a bigger value. So f prime of -4 is less than f prime of 0. If I now go ahead and compare f prime of +4 and f prime of 2, so we'll go to +4 over here, and I have a horizontal tangent line, so that has a slope of 0. And at +2, if I find the function, there it is, that is a negative slope. So that 0 is bigger than a negative number, so that means that f prime of 4 is greater than f of 2. So we can just go ahead and put a little note for ourselves, right? This was 0 and this is negative. And then over here, both of these were positive, but we had to actually think about, well, which one is steeper, which one would be a bigger number. We'll go ahead and look at f prime of 6 and f prime of 8 now. So let's start with f prime of +6 over here. So if I draw my tangent line, this is what it looks like approximately. And then if I go over here to 8, and find the function up here, and I draw that tangent line, it's actually going to be a steeper line over here at the x value 8 as it is over here at the x value 6. So if I think about rise over run, I know that it's kind of subtle. Maybe I should go ahead and redraw the one at 6 for a second, because that one would probably be just a little bit flatter. It's not perfect with my software, but we can see that the slope over here at the x value 8 would be steeper, would be a bigger number than here at 6. So f prime of 8 is the bigger one. F prime of 6 is less than f prime of 8. And then lastly, we'll go ahead and consider f prime of -6 and f prime of -8. So we'll go ahead and find -6 down here. And we'll draw our tangent line, just grazes the surface, and we'll go to the x value 8, find the function, and we'll draw our tangent line there. So we have both negative, right? We have both negative slopes here, but it's again a matter of comparing the steepness. Now, at -8, I do have a steeper slope than over here at -6, but we have to think about negative numbers. So let's say the slope over here, and I'm just approximating, maybe the slope over here is -4, and the slope over here is -2. So if I went ahead and just went with my approximate values, this f prime of -6 we said was -2, and f prime of -8 was -4. And if I think about which one is bigger, -2 is a bigger value. So again, it's just an approximation. This one's the way that I've drawn it, it's actually more like a slope of -1. But this one maybe could be a slope of -4. So it's again just to help us figure out which one is the steeper slope and which one is the bigger or the smaller number.